workbook, physics, and fields, and magnetic fields. Where's my slides? Hey, Siva. Oh, good. They didn't delete. Here they are. Come on, open up. What's taking so long? Oh, I see your breakfast in there. A big chocolate cookie, huh? Yeah. I like your bag. Where'd you get it? Pennies. Ah, kind of cool for pennies, isn't it? Bargain price? Good price? Yeah. Pennies is great. Have you shopped there, Andak?
Yeah.
It's good, isn't it?
Yeah.
Which ones do you go to? On O'Connell Street?
Yeah.
Yeah. Is that big? Pretty big, isn't it?
Yeah.
Oh, come on. Going so slow. It hasn't opened the PDF yet. Sorry guys, I don't know what the delay is. It's taking a while to open this PowerPoint. Oh, here we go, something's happening. Whoa, slowly. Sorry. Any of you going back home next week? Staying here? Oh, she sounds sad about it. Did something change? Change your plans? Huh?
I won't study.
Ah. You'll have too much of a nice time, huh? Yeah. Okay, magnetic fields. It's a big enough topic, this one. Can you see it okay? Yeah, alright. You got that? Yeah. Yeah. So, there's quite a bit to do. Anyways, you all know what a magnet is. I mean, you probably played with them when you were little children. So the magnetic field, we looked at this word already, field. Do you remember exactly what we mean by field? Do you remember what it is? It's like a vector field is something around. It shows you the direction. Anyways, the magnetic field is the area around a magnet where there's a magnetic force. And, okay, so I don't think you need necessarily the next sentence, but you do definitely need the third sentence, which is magnetic fields can usually be seen by magnetic flux lines. Yeah, no, I think that's enough. Don't bother with the second sentence. It's just a bit of a link. got that, Andek? You got that, Siva? Yeah, I'll just, if I can, just draw you a picture. Oh, what is going wrong here today? Oh, for goodness sake, come on. Right, here we go. Here we go. Okay. I'm so sorry, this is terrible. I don't know what is going wrong with the computer today. Here we go. Right, here. Come on. I'll just have to use my mouse. It'll be ugly. Magnet. North. South. Okay. So, when I say the magnetic field, we kind of draw it like this, going around the magnet. I'll have a picture. I think you might have seen, sorry, you might have seen pictures like this before. Do you know what I'm trying to draw? Yes, good. Those blue lines there, they're the ones that are called the flux lines. Okay. All right. Let's continue. Come on. There we go. Ah, beautiful, beautiful. So, that picture is of the magnetic field, and those lines are called the flux lines. And they sometimes ask you to draw this in the exam. So if you can copy that in your notebook, please. Got that? Is Matt doing something on Tuesday nights? He seems to be late Wednesday mornings.
He has a job now, I think.
He has a job?
Yeah.
I was just wondering that. So where is he working? Restaurant?
Sure about that.
Takeaway? No. And Kim, she doesn't have a job, does she? Or does she?
Not sure.
Do you know she has a job? She's just sleeping now. Okie dokie. Continue? You got that drawn? So like I said, they sometimes ask you to draw this in the exam. What's happening? Oh, for goodness sake. Whoop. Now, the Earth has a magnetic field as well, which you probably knew this already. What confuses people sometimes is that they think, because we call this the north, this is the north part of the magnet, it's actually upside down. It's like here's the north and here's the south. The reason we call this the north pole is because if you had a small magnet, you remember opposites attract. So on the top it must be south because the north part of your magnet would point up. Do you know, like, you've seen a compass before, haven't you? That's not too old, is it? You've seen compasses. So they have a north and a south. So if the north is pointing that way, up to the top, then it must be because there's a south magnet up at the top. So although we call it the north, there's actually a south magnet up the top. Do any of you have a compass at home? But you've seen one before?
Yeah.
Like in real life or on TV?
Really?
Real life, okay, that's good. Again, I need you to draw this. Can you see that the north is down here and the flux lines, they go around and up like this. You drew that? It's actually very important that the Earth has a magnetic field because it gives us some protection from the sun. And interestingly, I don't think any other planet in our solar system has a magnetic field. I think it's only the Earth. And the reason for it is because in the center of the Earth there's the iron, you know, the molten iron core. Okay, continue. Yep. Well, Matt, you made it. I was wondering with the students if you are working late on Tuesday because you're usually late on Wednesday. And they told me you had a job. This is true? Sunday, yeah. Where are you working? Restaurant? Takeaway? Which one? Any free noodles? Where's Noodle Bar?
Huh?
Where's that?
The big one.
City Centre? Okay. Oh, this is stuck. So what do they have you doing? Are you cooking? Are you cleaning? Are you a waiter? What are you doing? Okay, great. At like the counter? Yeah, okay. Alright, next now, another picture for you to draw, I'm afraid. So, what's interesting is when you have a current can actually make a magnetic field. And you can see this with a very simple little experiment. So here, there's no current, and all the magnets point to north. No current. But then when you turn the current on, you'll get a magnetic field that goes around the current. So you can see all the magnets now point in a circle. And, well, I'll tell you more in a moment. But if you can draw, you don't need to draw this one, but if you can draw this picture here. You get free food, Matt? They give you free lunch? That's good. My first job was in McDonald's. It's much better serving customers. It's too hot in the kitchen. It's not pleasant. That's good, Matt. If university doesn't work out, you always have a backup option. If you don't get your maths or physics grade, you have second choice. Yeah. Yeah, no, I'm just joking. Alright, you drew that? Yeah. So what I was going to say is, you have this rule, I don't know if I have it on the next page, I might actually have it on the next page. It's called Fleming's right hand rule, Fleming's grip rule. I don't know if you've done this one in high school. So, you take your right hand and you put your thumb, oh sorry, what has happened here with this picture? Oh, that's a bit messed up, sorry. As I was saying with this one here, you take your right hand and you put your thumb in the direction of the current, okay? And your fingers then will be the direction of the magnetic field, okay? So do you see here in that picture, if I was to put my thumb where the current is, then the magnetic field, it curls around where my fingers point, okay? So what you could do is, beside your picture here, you could just write underneath it, you know, something like, you can use the right hand rule, the right hand grip rule. Now I think I have a picture of it later, but just under this picture you could write, use right hand grip rule to find the magnetic field, you know, something like this. How many hours are you allowed to work on your visa? 20. It's kind of a lot, actually. Alright, continue. So, I don't know what messed up with the next slide. There is a way to make a magnet if you have a current and a piece of iron. Come on. Here we go. Okay. So, if you remember, we just said if you have a current, it makes a magnetic field around it. Okay. But if you bend the wire like this in the shape, we call this a solenoid, and you run the current through it, so the current goes around through it like this, what you make will be exactly like the bar magnet that we had earlier, whereas this end will be the north and this end will be the south. Okay, so if you want to make a bar magnet, but you don't have a bar magnet, you can actually just do it with a current and just have it looped around like this, and this will be exactly like a bar magnet. Okay, now usually what people do is they put a piece of iron, a piece of soft iron in the center here. It makes it work a little bit better, more efficiently. But you actually don't need to have the iron in the center. If you simply bend the copper wire around like this, you can make a bar magnet. Now again, they could ask you to draw this solenoid, so if you can do your best to draw this in your notebook, please. You don't need to draw this, you have this from earlier. It's just a solenoid. Drew that, Siba? Yeah. Okay. You need a minute, Anda?
Yes.
Yeah, okay. Got it? Okay, great. Can't see. Where's my mouse? Oh, there it is. Okay. Right. So we saw two things that we need to clear up a little bit. The last picture and how we can tell which way magnets will point. So the first one is okay. This is what I was telling you about earlier. This is called the right-hand grip rule. And this lets you work out which way the current will turn around the magnet. Yeah, we'll get to that one in a moment as well, yeah. The first one is just the grip rule, like this. Okay? The next one now, come on. What is wrong with this today? There you go. The next thing we have to do is just give the definition of a solenoid. So you can see it's quite a short definition. A solenoid is a coil. Actually, I'll ask you guys first. Does anyone know the name of the shape? The shape the solenoid was in. That shape. Does anyone know what it's called? What would you call the shape? Go on. A what? It's kind of like a cylinder, except it's not solid. So, what would you call that shape, see, that goes like this? No. Andy?
Coil.
Yeah. We can call it a helix. Is this a new word? The shape that turns around like this is called a helix. Or, informally, you can call it a spiral. But a helix is the precise name for it. Is that a new word or not? Is it a new word? You knew this word?
It is not a new word, but it uses something else.
Yeah, you would hear it used in DNA biology. In DNA, it's called a double helix. There's two of them. Okie dokie, you have that, Anda? Yep, okay. Now, continuing. So, it's like a spring shape. Okay. Right, now, we've talked a lot about the pictures, but we haven't said what units we're using yet. So, we need to know how to measure how strong a magnetic field is. So firstly, some definitions. The magnetic flux over a particular area of space is the number of magnetic field lines passing through that area. So I can draw, and the SI unit is called the Weber, which is the same as volt seconds actually. I'll just, maybe I can demonstrate that with my book here. So imagine I had a magnet and I had a magnetic field running this way, okay? And can you picture there were five flux lines. And those 5 flux lines, they pass through this area of space. So I would say this area of space has 5 Webers passing through it, meaning 5 flux lines passing through it, okay? So you realise the definition, it actually matters how big the area is. So if I was to make this area smaller, then I would say there are only 2 Webers passing through the area. Okay, so it's kind of like, I don't know, it's kind of like volume. You need to know how big the area is. So a Weber is just actually one flux line in the diagram. Okay, And it's interesting, the Weber is the same unit as a volt second. Not that you don't really need to know that. But you do definitely need to write this down, magnetic flux. And does anyone know the name of that Greek letter?
No.
Yeah? Anybody?
I knew that.
Nobody knows that Greek letter? I think somebody knows. No? See that? What? No? Phi. Phi. Yeah? Phi, yeah. Okay, you can write that down. Continue? You got that, Matt? Yeah. Well, I think it's just more definitions on this page. What is wrong? Come on. There we go. Load in. There we go. So the next thing is called the magnetic flux density, B, and it's for a point rather than an area, and it's the amount of flux per area. So what does this remind you of from mechanics? It's a little bit like pressure, isn't it? Yeah. So it's magnetic flux per area. So, and again, just like pressure, it's perpendicular. The unit is called the Tesla, but you can figure out the unit here from the definition. So what would be a Tesla if you were to think about the definition? Something per something. What would you say?
Flux per area.
Yeah. So what is the units for flux? Is Weber. And the units for area? Meter squared. So a Tesla is the same as a Weber per meter squared, yeah. Which is just 1 Weber per meter squared. And what would be the formula for the magnetic flux density here?
Flux over area.
Yeah, that's it. So just be flux over area. Okay. I think you probably need the whole definition. I'd say you need the whole thing. Okie dokie. We got all that super. Now, what I said at the bottom here, the B is the nearest thing we have which is like the E. So you remember we did electric field strength? The bigger the E, the stronger the field. Same deal here. The bigger the B, the stronger the magnet. Okay? So the B is kind of like the E. Can I continue? Yeah. Everybody's sleepy. Do you have class after my class? Who have you got?
Chemistry.
2 hours or 1?
2.
I see. Sleepy and tired. Okay. Now, a moving charge produces a magnetic field. So we saw earlier, when you have a current is a charge that moves, it produces a magnetic field. So because of that, it means a charge that's moving in a magnetic field can be pushed by the magnetic field because it produces a magnetic field and the two interact. So anyways, you know north repels north, south repels south, north attracts south, and so on. So if you had a magnetic field here and you had a charge that's moving, the charge produces a magnetic field, and this magnetic field interacts with this magnetic field and it causes a force, so it causes a movement. And there's actually a formula to calculate how much force a charge Q in a field B travelling at V will experience. And the formula is this. Now, this is a special multiplication. So QV cross B, it means QV times B, but these are vectors, okay? The V velocity is a vector. The B, the magnetic field, flux density is a vector, and force is a vector here. So what I'm trying to say is, there's two parts to this formula. Part one, how big is the force? The force is the charge multiplied by the speed multiplied by the magnetic flux density. But also we want to know what is the direction of the force. You know, if I have a charge moving this way and a field moving that way, which way is the force? Okay? So there's a special way to calculate the direction called the cross product. And you were showing me these rules earlier, yeah. So in other words, you can use one of these rules, these hand rules, to calculate the direction, okay? So that is a special multiplication. It's called the cross product. And it seems like you've seen it already from high school. Does anyone know what Andek's talking about? These hand rules? Yeah. It's a special multiplication on the cross product. But we use something called Fleming's left-hand rule. I'll explain the rule in a moment. What you need for this, I don't think you need to write this part down, but you do need to write the formula down, the definition here. Got that? Continue? Yeah. So, do you remember, Andek, how this left-hand rule works?
Force, field, current.
Very good, very good. You remember, very good. So, I have a picture as well. Can you see my hand, Matt? Yeah. So, you put your hand like this, and each part has a name to it. So, your thumb is the direction of the force. This finger here is the direction of the field. The field goes from north to south, and this direction here is the direction of the current. And you know that current goes from positive to negative, isn't it? Yeah. So I think I have a picture coming up. Yeah, good, okay. Do your very best to try and draw this. You don't have to draw the hand perfectly, you could just draw 3 lines to show the 3 directions. It's called the left hand rule, you should remember that. Do you draw beautiful fingers or little lines? Lines, yes. Got that on deck? Okay. So let's see. Oh, and if you're wondering, there is a right-hand rule as well, which we'll do in a later lesson. Do you know the right-hand rule? What it's used for? Yeah, because sometimes in high school you only learn about the left-hand rule, but there's actually another situation where we use something called the right-hand rule. So of course it's easy to mix this up in the exam. Right. Here's our first example. A bar magnet has a flux of 2 Webers, and the region where the 2 Webers pass through is a circle of radius 1 centimetre. What is the flux density? Okay, so which formula are we using here? Which one? Yeah, it's flux over area. Do we know the flux? We do, 2 Webers. And how can we calculate the area? Pi r squared, yeah. Alright, so I think you can do this easy question for me. Can you give me the flux density, please? You got that? Calculate, what did you get, Andek?
0.64.
Yeah, it should be small because the area is small. Oh, wait, hang on. That sounds a bit no, it should be big actually. What did you get, Siva?
6, 3, 6, 6, 5.
And what did you get, Matt? Okay, I think you must have mistyped something, Andek. Did you type it upside down perhaps? So on the top you have 2, and on the bottom you have pi 0.01 squared. Huh? No? Yeah? Andek?
Yeah.
What happened?
I was off by a few.
Yeah, is it because, did you?
Because I didn't change it in centimeters.
Ah, okay. Continue?
Was the answer?
Yeah, what was the answer, sorry?
6366.
6366, and the unit? Tesla, yeah. Okay. Let's do a harder one now, maybe. Is that okay, Andek?
Yeah.
Are you sure?
Yeah.
Okay. Come on. Come on. Oh, too far. Here's one where we have to practice our hand rules. A proton moves towards the east. What is the direction of the force due to the Earth's magnetic field? So, let's see. Which way is east? That way? You got a compass? Well, I thought that way. Okay, all right, fine. So if that's east, then this way is north. This way. Yeah. North is. Oh, okay, it's a bit of an angle. All right, let's make it easy for us. Let's just pretend that way is north and that way is east. Okay. So if I draw the Earth's magnetic field, which way do I draw the lines? Do I draw them going that way, or do I draw the lines going that way? So, no, actually, this way. Because the thing that's confusing about the Earth's magnetic field is we call that north. Wait, which way did you say? Okay, sorry, I think you were right. Sorry, apologies. We call that north, but then when we picture the Earth's magnet, it's like a big magnet where this side is south and this side is north. And we draw the field from the north to the south. So the field is going that way. Okay? And if the proton is heading east, the proton is going that way. So the current is going that way. So I use my left hand rule now. This finger is for the field, so that's that way. This finger is for the current, which we said is to the east, which is that way. So the force is up. Okay? So what will happen is, if the proton is moving this way, it will feel a force that causes it to turn up. It will increase in its height. Yeah? So this is using the left hand rule. So the answer for this is the proton will climb up. It will move up. It will rise. Is that okay? Yeah. Actually, I should show you some picture here, or might come up. It's kind of difficult to draw in 3 dimensions. Guys, can you look a sec? I just want to draw a picture for you. So if I want to draw a picture, the magnetic field heading up, that's fine. That's going up. That's going down. That's going right, and that's going left. That's fine. But because we're dealing in 3 dimensions, we need a way to draw out and into the page. Now you could try and draw it 3-dimensionally like this, you know, but it's not quite easy. So what we do is we imagine that we have an X, we have a Y, and we have a Z here. But you can't see the Z because you're looking straight at it. Do you understand? If we want to draw in and out, we do it like this. So, like I said, this is up, down, left, right. This one here is out of the page, and this one here is into the page. So if I draw a dot and a circle, it means it's coming to me. And if I draw a circle with an X, it means it's going into the paper. Have you seen these symbols before? No? They're new symbols? Okay. I'll tell you how you can remember. This is how I was told. Do any of you play darts? You know darts? You know this game though. So if you could imagine the dart was coming at you, it would look like a dot with a circle. But if you were throwing the dart on the wall, you would see like a cross because of the little wings on the back. Okay? So this is how you can remember. So that's out of the paper into the paper. I think you should draw that down. This is a new symbol for you. Have you not seen this before? No? Okay. Now, I think I have one more question, but it's a hard one. I think I'll probably do it. Yeah. So, an electron enters a magnetic field and then experiences a deflecting force. The magnetic flux density at the location of the electron is about 250 millitesla. The electron was moving at 1/10 the speed of light when it entered the field. What is the acceleration of the electron due to the field? So I'll draw what's happening here. Be easier. So here's your electron. And it's moving along here. And then it enters a field. It doesn't really matter. I just care that it's perpendicular. So we'll just, we'll draw the field like this. Okay. Now, what did I say it was? This is 250 millitesla, and the electron is traveling at a speed, is 1/10 the speed of light, I said in it. So, before I begin, what I want you guys to tell me, I'll let you think for a moment. I want to know which way the electron will move. So I want to know what is the force here, using the left-hand rule. Okay, so have a think. How many did you get? Good. Say again? The red lines? That's the field, magnetic field. And the blue is where the electron moves.
Wait, so that's the red line?
Say again?
The red line?
Is the magnetic field. The B. The B in other words.
Yeah.
So which way will the electron move?
This way.
So describe it. It'll move up the page, down the page, in the page, out the page.
It's like the blue one's moving outwards, so.
It'll move out to you.
No, not. The blue one seems like it's moving outwards.
No, the blue one is just moving right, and the red one is moving up. So the electron will either move into the paper, or maybe it'll move out of the paper.
What is that?
Huh? Just the movement of the electron. The electron's moving to the right. Okay, let's see. So let me show you. Watch carefully. Right. The one we definitely know is the magnetic field. That's definitely going up. So first things first, point that out. Now, the current. So right now my finger is pointing to you. This is wrong. That electron is not traveling to you, is it? It's traveling to the right. So you might think, oh, I put my finger here. But no, that's wrong. I was trying to trick you. It's this way. Because remember from electricity, if the electron moves from A to B, we say the current is B to A. Do you remember that? Yeah. So actually my hand is like this. The field is up, the current is to the left, and so the force is into the page. So if I was to draw the force on this picture here, when the electron hits the magnetic field, there's a force into the page. So the electron is going to come along here and then swing into the paper. Yeah? You don't look happy with that. You look confused. Is it okay? Is it okay? Or maybe I did it wrong. Sorry. Let me try again. Okay, we all agree that this finger should be up. We all agree with that? And do we agree that this finger should be left? We agree or disagree? Remember, this one here is for the current. So my thumb is pointing into the page. Your hand, turn it this way. There we go, that's it. Yeah, that's it. Field up, current left, so force in. No, you need to turn your hand more this way, this way. There we go. Okay, let's calculate. So what's the formula I use to calculate f? What is it? Yeah, Q V B. The Q is the charge of an electron. The V is 1/10 the speed of light. And the B is 0.25 Tesla. I don't remember. What was the value of E? I keep forgetting it. 1.602 times 10 to the minus 19 times 0.1 times 3 times 10 to the 8 times 0.25. So when you're ready, you can tell me what you get here. I don't know, it'll be something along the lines of 10 to the minus 12 newtons. Oh man, nice, okay. Now, but I didn't ask you for the force, did I? I asked you for the acceleration. So what do I do next now? How would I get the acceleration here? Yeah, so you can say F is ma. So to finish, to get the A, I just take my answer and divide it by the mass of an electron, which is, what is it, 9.11 times 10 to the minus something, 31. Okay, so if you put that in now, what do we get? $18, huh? Like that? Okay. Can I close this? So what I want to do, we'll do the second lesson in 5 minutes. It's not going to be as big as this lesson. There was lots of new things in this lesson. So if you can just, how many questions did I give you actually? If you could do 1, 2, 3. No, don't even worry about 1 just yet. You can do 1 at home. If you can just do 2 and 3 now, and then we'll go on to the next lesson. So just practice 2 and 3 for me for now, and then you can finish them at home. You got the page, yeah?